is by Richard Crooks from Texas A&M University. Are we having a change? Do I have Kim?
Yes, correct.
Oh, all right. My mistake here. My book is wrong. We have Mr. Kim is going to present the paper on some self-assembled monolayers. Sorry for
The title of my talk today is Synthesis and Characterization of Self-Assembled Monolayers of Omega-Functionalized Organomercaptans containing diacetylene functional groups. And this work is supported by NSF and DOE. Self-assembled monolayers receive great attention these days. First, a single crystal quality organic thin films can be made by this approach. And second, modified surfaces can be used to study surface interactions, and those surface interaction study can be used to design chemical sensors. When biomolecules approach to the substrate, whole substrate, the subhead groups are tightly bound on the surface by chemisuction. Then alkyl chains are aligned by van der Waals interaction. Then, to maximize those interactions, the alkyl chains are tilted 30 to 40 degrees to the surface normal. And also, terminal functional groups also support those packing process to provide more stable and more durable monolayers. The molecules containing polymeric backbone structure was investigated. The polymerization of diacetylene was first discovered by Reagan in 1969. And by polymerization, those long conjugated and highly oriented structure are supposed to exhibit highly nonlinear optical properties. But those single crystals are very hard to grow. The longer braided films and the organometallic crystals were studied as alternatives. The longer braided films, by polymerization, normally give about 10% reduction on the surface area, so it leaves a large defects on the monolayer films. The organometallic crystals, the distance between diacetylene molecules are normally determined by the interlayered metal ions, so only a few showed a satisfiable result. And also, those polymerization of diacetylene has been used to study polymerizable phospholipid. Because they polymerized in the solid structure, the packing of diacetylenes, which resemble the structure of polydiacetylenes, is preferred to minimize the distortion. For example, the distance between molecules in polydiacetylene is fixed at 4.93 angstrom. So to be polymerizable, the distance in the diacetylene molecules is supposed to be plus minus 0.2 angstrom of distance E2. And also to improve the reactivity of a one-port cross addition of diacetylene molecules, the tilted structures are preferred. Those requirements are fully supported in the latest structure of a self-assembled monolayer. First, the distance between the molecules are almost fixed at 4.99 angstrom, which is very close to the distance D2 of a polydiacetylene. And the tilted structure of self-assembled monolayers give a good environment to polymerize the diacetylene molecules. Based on these model studies, we synthesized the molecules containing diacetylene. Normally, the diacetylene functional groups are synthesized by coupling to acetylene terminal groups. Unfortunately, the thiols are very reactive to that reaction condition, so we decided to have diacetylene moiety in the beginning of synthesis. Commercially available is trimethylsilane diacetylene was converted to diacetylenide and reacted with the alkyl bromide to introduce one alkyl chain on one side of diacetylene. Then this diacetylene converted to diacetylenide again and reacted with the dibromodecane to introduce another alkyl chain on the other side of diacetylene. The alcohol functionalized diacetylene was obtained by deprotection of previous molecule. Then this alcohol is easily oxidized to carboxylic acid. So both functionalized diacetylene, the bromide groups are successfully converted to the thiol functional groups in presence of sodium hydrogen sulfide. By the position of these thiol molecules on the gold, first the presence and the packing quality of these films can be monitored by FTIR external reflectance spectra. Then the polymerized chains, the polydiacetylenes, are known to absorb light in the visible range. So the formation of polydiacetylene chains can be monitored by UV visible spectroscopy. When they make a long fully conjugated chain structure, they're supposed to known to absorb light in 600 to 630 nanometer region and appear as a blue polymer. And further exposed to UV light or exposed to the excessive heat, those long conjugated chains have some conformational change, so appears as a red polymer which absorbs light at 540 nanometer region. Unlike Langmuir Brothers films, these self-assembled monolayer on one side of alkyl chains are tightly bound on the surface, so we expected that conformational change can be limited in this structure. And any defects, density defect changes, or the craft changes can be easily monitored by cyclic voltammetry or in situ scanning tunneling microscope. The bottom figures explains the typical selection rules of IR. And as was mentioned, only the p-polarized instant light generates a reactive dipole moment change in the direction to the surface normal. So based on these FTIR studies, we can tell any tilted angle changes by polymerization or reorientation of the functional groups. But unfortunately, the diacetylenes are very almost inactive to the IR spectrum. Also, these conjugated polydiacetylene chains are aligned parallel to the surface, so we didn't expect to observe any significant peaks in the FTIR spectrum. When carboxylic acid terminated, diacetylene thiols are deposited on the gold. They observe this asymmetric and symmetric stretching of CH appeared at 2926 and 2853. This actually shows this film is more liquid-like quality. And we explained that by this big rod of diacetylene exists in the middle of the packing, so may disturb some packing process. And the carbonate double bond stress appears here, and single bond here, and COH bindings appear 1420. By exposing this film to the UV light, the CH stretching regions are remain almost same, and only CO double bond stretching region appears about 20% reduction of intensity. So we expected they should have some orientation changes on the terminal group. Then, for the exposure of these films to the UV light shows no significant changes. So we expect the polymerization almost completed at this point. The alcohol functionalized diacetylene thiol shows a slightly different result. First, the symmetric and symmetric stretching appeared at 2923 and 2853, and by exposing to the UV light, the peaks are shifted slightly, and then the intensity of peaks also decreases slightly. Further exposure of these films to UV light shows very interesting result. That CH stretching regions are stayed almost same, but the alcohol functional groups shows some oxidations. So part of alcohol looks like oxidized to some aldehyde or carboxylic acid. To confirm this oxidation, we introduce a small amount of oxygen inside of this reaction system. Then all alcohol functional groups are converted to the carboxylic acid and the aldehyde. We are currently working on controlling this oxidation chemistry. As was mentioned, the polymerization can be directly monitored by visible spectroscopy. By using alcohol functionalized diacetylene as a background, by exposed to the UV light, we observe intensity changes in the blue polymer region. Based on this time versus observance curve, the polymerizations almost stopped at about 7 minutes, and then further exposed to UV light doesn't show any significant intensity changes. This spectrum shows even after 7 minutes exposed further to the UV light, the peaks, maximum absorption peaks are stayed almost same position in the blue polymer region, which is expected because the conformations of polydiacetylenes are limited by the tightly bounded subcategories. And the carboxylic acid terminate diacetylene shows a similar result, only take a little bit longer to complete the polymerization. So based on this result, we are very interested about the chain length, the effect of chain length to the conformational change on the polydiacetylene. We try to develop multi-layers of these diacetylene molecules. The preparation of a multi-layer of carboxylic acid terminated thiols are reported by Ullmann's group in 1991. So first we deposited carboxylic acid terminated diacetylene thiol on gold substrate. Then exposed these carboxylic acid terminal groups to the cupric perchlorate, converting this carboxylic acid to the cupric perchlorate, cupric carboxylate. And when these copper ions exposed to the carboxylic acid terminated thiols, they selectively bind on the thiols. Then the terminal groups are carboxylic acid terminated double layers are formed. If you repeat step 1 and 2 several times, the polydiacetylene, multi-layers of the diacetylene are formed, and we observe the changes of intensities by exposing this film to the UV light. By the intensity changes versus exposed time to the UV light, this film shows a lot faster polymerization. It completed its polymerization about 120 seconds. Then the major changes after that is just shifting of absorption maximum. Interestingly, even after 300 seconds exposed to UV light, still some part of absorption is remaining in the over 600 nanometer region, which is known as a blue polymer. And major part of the peak is shifted to about 500 nanometer region, which is known as red polymer after conformational change. The layer capacitance measurement was used to monitor any changes on the monolayer surface. The capacitance is known to be proportional to 1 over d. So when the ionic layer, the distance between the ionic layer to the metal surface increases, the capacitance is supposed to be decreased. And when the distance is decreased, the capacitance is supposed to be increased. So when the alcohol and the carboxylic acid functionalized biacetylenes are coated on the electrode, then exposed to the UV light. Interestingly, both shows a decreased capacitance. This result can be explained by the changes of rigidity. When the molecules stays as monomers, they are more flexible, so the ionic layers can enter inside of the film. So the average distance between ionic layer to the metal surface is smaller than distance between D2. After polymerized, they become rigid, so ionic layers are supposed to be stay on the top of the monolayer. This increase of distance was resulted as a decrease of capacitance. Also, phenol density measurement was used to monitor the defect density. When monolayer covered surface on the electrode has no defect, the redox molecules cannot enter to contact the metal surface. Then these monolayers, these systems normally shows typical to the tunneling current. And when there is a few small defects on the monolayer, and then these defects are spaced far apart, so the diffusion layers doesn't overlap each other. Then the cyclovoltammograms typical for the radial diffusion was observed. When there is a few large defects or lots of small defects spaced very closely to each other, then cyclovoltammograms typical to the linear diffusion was observed. When ruthenium hexamine was used as a redox molecule, and alcohol and the carboxylic acid functionalized diacetylene covered surface, both shows reduced defect density by the polymerization. This result also confirms the polymerization process doesn't make any damage on the thiol films, and also proves this kind of measurement can be used for further study of diacetylene covered films. The direct surface property changes was monitored by the in situ scanning tunneling microscope study. The number one image shows the typical image for alkyl thiol covered gold, and lots of pitch are shown. These are typical for the alkyl thiol covered surface, and also you can see a step, one gold top step here. And number two is the carboxylic acid functionalized diacetylene thiol covered gold, and you can also see some pitch around here. By exposing this film to the UV light, the surface shows a dramatic change. After 20 minutes to the UV light, the films appeared as a very smooth. Most of pitch typical to the alkyl thiols are almost gone. So we expect at this point maybe the cross-linked polydiacetylene chains may change the property of this film. We try to apply some alkyl thiol damaging conditions on this small boxed area. This boxed area is about 50 times 50 nanometer area. After about 4 scans, and zoomed out and see the area again, they actually shows no changes at all on the surface. If you apply the same conditions to the alkyl thiol covered surface or the diacetylene covered surface, both shows expanded pitch and also appear there's a rock on the surface. Encouraged by this result, we try to apply even severe conditions to this epoxy area again. When you put the higher bias voltage, about 3000 millivolts, and the fast scan rate to this epoxy area is the same area I showed you before. Zoomed out and see the area again, they leave about 4 angstrom deep squared pit. These etching conditions applied to the regular amplifiers cover the surface also leave about 6 to 8 angstrom deep squared pit. All these results also support the enhanced rigidity of this film, and the amplifiers are still present after polymerization process. To conclude, we first synthesized the functionalized diacetylene thiols, and the property changes were monitored by several different analytical methods, and we are currently working on the possible application of this polymerization study to the photolithography. Thanks for your attention.
Right, do we have any questions? Yes.
In the case where you had before and after polymerization, have you done any say, infrared measurements that would show more gauche bonds within the unpolymerized than the polymerized one, or something along that line?
We simply used the FTIR method to monitor the changes of functional group orientation, and
that's the terminal, the carboxy group.
Yes.
Or that CO stretch.
And also,
in alcohol.
as you can see, when the tilted structure of these molecules are changing by polymerization, we expect there may be some changes of interactions of CH stretchings by polymerization. But in carboxylic acid terminal group, functionalized diacetylene actually shows no intensity changes, and the alcohol covered surface shows some about 10% decrease in the intensity. So actually we cannot tell clearly about how much structure changes occurred in the surface, but for the alcohol functionalized diacetylene shows a 10% decrease. We can tell the tilted structures are
But you can
more
also get
vertical.
this information more or less by looking at the CH2 asymmetric and symmetric
Right.
stretches and doing some vector analysis or something more complex. But I was wondering whether because that'd be the more classical way of looking at tilt.
Unfortunately, in these thin films, there is some limitations because the molecules are covered just by single atomic layer, a single molecular layer. So the intensities are pretty weak. So any Gaussian or anti-structure changes is very hard to observe unless you make high multi-layer films, and you may study some changes on them.
Yeah, thank you.
I was wondering, it looks like these films might have some interesting properties as far as their frictional characteristics relative to the other unpolymerized monolayers. I was wondering if you have done any experiments to look at, like, maybe at the interface, you polymerize one area and then did force microscopy across the interface, whether you could tell a difference in the friction between the two different regions.
We actually tried the rigidity changes by the surface acoustic wave device in the Sandia National Lab, and they show some rigidity changes, but I didn't get the clear data on that, so I couldn't tell you any result. And we didn't check any force microscopic study on that.
Yeah, yes, we.
The polymerization, that's done in air or in vacuum?
This is all done in the nitrogen interface or argon, on the argon atmosphere.
So when you transfer over to the STM to look at these films, you transfer in air or in nitrogen? What is the effect of oxygen oxidation on these films?
Yeah, we actually started in the beginning by the transferring films one by one, but after that, we couldn't get to the same area by the polymerization. So we developed a polycarbonate boxes, which we can put everything in it, and it's filled with argon, and we put the gold balls covered with molecules before polymerize, and then you scan the surface, and then you polymerize there, and then you scan again.
So an oxygen-free environment.
So there is actually no oxygen present in the system. We filled up that system with argon at least 5 minutes before any experiment.
And when you do your UV Jones measurement, is that in the same configuration that you're doing in the collecting biology?
That is not the same. They are different.
What are you doing then? How are you doing
The FTIR experiment was done by the reflectance spectra, so you can use gold-covered silicon substrate, so the molecules are covered on that. But unfortunately, we couldn't get the reflectance individual spectrum, so we need to use a transition method. So I developed a method to put quartz substrate, quartz crystal, and covered with the gold on both sides of that, and deposit the molecules on it, and use that substrate for individual spectroscopy.
So it's transmission or?
It's transmission. So for the individual, it's transmission. FTIR is reflectance.
And when you take these films out there, and this will be my last question, do they undergo oxidation thoroughly?
After polymerization, all the systems become very stable. So, and those oxidation reactions are caused by the UV light, which oxidizes the oxygen, convert the oxygen to the ozone, and that ozone, I think, is very reactive to the alcohol, convert some alcohol to the aldehyde. So when you fudge the system with argon for a pretty long time, you actually cannot see the oxidation, and you introduce a small amount of oxygen on it, you can see oxidation in less than 1 minute. So, but still we cannot control that reaction right now. We are still working on it.
Yeah.
Why do you think the concentration of etch pits goes down after you UV irradiate the film?
Yeah, I need to. This etching condition is normally used to open some windows on a monolayer covered surface. So this is using STM tip-induced lithography.
No, I mean, well, before you irradiate the film, you see a lot of little holes, which indicate there are etch pits in the gold.
Oh, right, the pit.
And then after you irradiate, the etch pit concentration is way down, it looks like.
So
why do you think that happens?
I actually am not an expert in the STM. This every works are done by me, but this STM works are done by me and the Incheon. We are postdoc in our group. And after this surface changes, we can see some surface changes happen. And this is smooth on the surface. Still, we cannot tell about what's really happened, because the explanation for the pits on the archive files on the scanning tunneling microscope still is not clear. So they are not clearly defined what that is. So the only thing I can tell It's
I think it's clear what they are. It's
Really?
not clear exactly the mechanism by which they form.
Sorry, I am not so good in explaining the STM image, so I couldn't answer that.
Larry, yes?
How many layers are your multi-layers? And do you think, or what do you think is the number of times that you can repeat that multi-layer forming procedure to still maintain the layers?
Yeah, I measured the growth of multi-layers in the ellipsometer, and they are multiplied by the number of thickness of monolayers. And
How many times did you actually repeat the procedure? How thick did you actually?
that's about 4 times. The reported paper, the Ullman's group actually made about 6 layers of the carboxylic acid thiols.
Yeah.
And I made just 4 layers, and the substrate is covered by gold on both sides. So actually this film is about 8 layers thick before we do the visible spectral study.
Is there any indication that the layer quality goes down as you keep building them up, or the states are very good?
Yeah, for this invisible, we do this experiment. We borrow the other group's invisible spectrometer, and so we cannot actually construct some modified system to study this experiment. As soon as we got some better instrument and by more chemistry, I can tell something better on that. But clearly on this result, I think not a big change happened compared to monolayer polymerization.
Okay, well, we will reconvene this symposium tomorrow morning at 8:30 when